again. In this example, you will practice the identification of statical classification and stability. We're actually going to look at 4 separate structures and see what we can come up with. First one here is this arch that has a shear release right at the crown, pin support at the bottom left, and a fixed support to the bottom right. We've got 2 reactions down here, and we've got 2 reactions, or rather 3 reactions down over here. So in and of itself it is stable because we don't have any concurrent reactions. Now whenever we have internal releases in our structure, we want to make sure that we cut it apart. So at the shear release we will go ahead and cut that apart, and then we'll just go ahead and sketch the free body diagram for both sides. So here's our reactions there. Once again, our reactions here. So this constitutes 2, this constitutes 3. And then the internal forces, because it's a shear release, we would have axial and moment still present right there, and that constitutes a total of 2 unknowns. So the total of unknown forces, count them up, we get 7. The number of structural parts, since we made 1 cut, that gives us 2 parts, and the total number of equations of equilibrium that we have would be 3 equations multiplied by 2 parts. That is equal to 6. So in this case F is greater than N, so that means we are statically indeterminate. 7 minus 6 means that we are statically indeterminate to the 1st degree. So we are stable and statically indeterminate to the 1st degree. Let's go to this next one. It's a frame. Let's go ahead and sketch what these reactions would look like. And one thing to be cautious of here is we start looking at all the reactions, and you can draw lines, projected lines, through all the reactions, and what we notice is that we get a point of coincidence on all this. So the reactions are coincident to the left pin. That allows this entire structure to pivot about that left pin. As such, without doing any computation, looking at any calculations, we can classify that as unstable, and once again that is because reactions are coincident. Next structure is a frame. And the problem we have here is that we have what we call a closed loop. And we cannot assess determinacy when we have closed loops. So what we want to do is we want to go ahead and cut that apart. And if we do that, we can get free body diagram that looks like this. Let's go ahead and sketch what these internal forces look like here. So we have shear, axial, and moment at each of those cuts. Okay, so in each of these locations where we made the cut, that constitutes 3 unknowns. 3 unknowns. And because we have these reactions here, so vertical, horizontal, and moment, we can then just make it easy on our free body diagram here and just sketch 3, 3, 3, because those are all fixed supports. And so if we count this up, total number of unknown loads is 1, 2, 3, 4, 5. So 5 instances of 3, so that is 15 unknowns. We made 1 cut, which creates 2 structural pieces. And so we have 3 equations of equilibrium per piece, 2 pieces. That gives us a total of 6 equations of equilibrium. So that means 15 is greater than 6. So we are statically indeterminate. And 15 minus 6 is equal to 9 degrees statically indeterminate. We are stable on this because all of our reactions are not parallel, and they definitely are not all concurrent. The last structure we want to look at has a number of springs and also a couple of moment releases. And so, as always, we will make cuts wherever we have internal releases. And we'll go ahead and sketch what the free body diagrams look like for this. Remember, we've got the springs here. And then we've got spring here, spring here. So for translational springs, we get one unknown reaction there. At the end of the moment spring, we get a moment, and then the pin support has this. At the moment release, these are internal forces. Okay, and so each of those constitutes two unknowns. So we can go ahead and count that up. Total number of unknown forces will be 10. Total number of structural parts is 3 because we made 2 cuts. Total number of equations of equilibrium, 3 equations of equilibrium for each part, 3 parts, so a total of 9. 10 is greater than 9, which means we are statically indeterminate to the first degree. We are stable because our reactions are not all parallel. See, like that? And they are not all concurrent. They're not all acting through the same point. So that concludes this example. As always, it is a beautiful day to study structure.